All right, so let's start. So there was one question last time about the max cut of whether instead of maximizing, so let me try to pull that up. Yeah, so recall that the max cut could be obtained as the solution to the following optimization problem. So it's argmax x in plus minus 1 to the n of x transpose Lx, where L was the Laplacian. Right? So the question was, well, instead of using the Laplacian, can we directly formulate it in terms of the adjacency matrix? And indeed, the one that maximizes or the x which achieves the max cut is also the solution to arg min of x transpose Ax. Mainly because if you look at x transpose dx, so L, remember, is just d minus A. So so if you take x transpose dx, that turns out that D is a diagonal matrix, and therefore all you get is some scaled version of the sum of the degrees, right? But of course it doesn't, so the value of min of x transpose Ax does not give you the value of the max cut, whereas this gives you the value of the max cut. One of the reasons why we look at the graph Laplacian instead of the adjacency matrix, as it turns out, is that this Laplacian matrix has some nicer properties. Of course, just as you have the adjacency matrix, the Laplacian is also symmetric, but it turns out that it has this nice property called diagonal dominance. So the diagonal entries basically dominate each row, because after all, it's the sum of the degree, right? So the diagonal entry will basically be equal to whatever minus the sum of the other entries of any row or the corresponding column. Now, what this gives us is that this matrix will have some nice properties. It's positive semi-definites, which means that all the eigenvalues will be non-negative, and particularly when you look at relaxations of the max cut problem, the graph Laplacian is more useful than the adjacency matrix itself. But in principle, you could go ahead and just use the adjacency matrix itself, and you could end up with the same solution if you are trying to maximize it or try to find the max cut exactly.
That's guaranteed though.
That's guaranteed, yes. So it's the same. The problems are equivalent, but of course the value of the minimum doesn't give you exactly the value of the maximum. It will be shifted by a certain. That's the only. Right. Okay. So, any questions before we proceed? So we were discussing some basic real analysis in the last class. A recap of many things, but maybe some new things as well. We saw subsets of the reals. So what do you mean by the supremum of a given set of real numbers? What is the infimum? What is the maximum? What is the minimum? Right? Remember that the maximum is not necessarily the same as the supremum, and the minimum is not necessarily the same as the infimum. If you take any subset of real numbers, it will always have a supremum and an infimum. Any bounded set will have a supremum and an infimum, but it need not have a maximum and or a minimum. Right? And then we saw what is a function, what is a domain, the codomain, the range, the image and the pre-image of a particular set, what kinds of functions are there, and this notion of finite and infinite. You can have countable versus uncountable sets, and then we talked about what a metric is, right, or a distance function. So a metric is any function which takes two numbers and returns another real number which satisfies these three properties. Right, so this metric in some sense generalizes the usual notion of the Euclidean distance, and this could be defined over more weirder sets. Right, so not necessarily subsets of reals or even Rn. Right, and Okay, then we went into what a neighborhood is. So a neighborhood, one way to think about a neighborhood is basically it's just an open ball, right? In the over the real line, a neighborhood is essentially just an open interval centered at a particular point, whereas in Rn it's basically just an n-dimensional open ball centered at a particular point, right? And we use this concept of a neighborhood to define what is called an interior point of a set, right? So basically we want to distinguish between points which lie on the boundary of a given set versus those which lie completely inside the set, right? So in some sense, an interior point is one where there is some room to go to the boundary. So basically the interior, so a point is an interior point if it satisfies the following property. There exists some open ball around that particular point and is completely contained within the set, right? And in particular, if you take a finite set, then the finite set does not have any interior points. Similarly, if you take a countable set, the countable set does not have any interior points, right? And a set is said to be open if every point of the set is an interior point. For example, if you take the closed interval 1, 2, there exist 2 points at the boundary, right? 1 and 2. And 1 and 2 are not interior points of the set, closed interval 1, 2. Right? So this set would not be open. But if you take the open interval, then, I mean, as the name suggests, it's an open set, right? Because no matter which point you pick, there is always some room to go further ahead. Right? You're not really at the boundary. No matter which point you pick, you're never at a boundary point in some sense. Right? Any questions? Yes.
For example, parabola. So
Okay.
parabola.
Okay. Okay. That's a function.
Will there be interior?
What do you mean by interior points? Right? It's a. So are you viewing the parabola as a subset of R2? Okay, so in that sense, it's in some sense like a one-dimensional curve in R2, right? Now, if you take this set, you draw a ball of whatever radius. Can you find a ball in R2? Basically, that's a circle, right? So can you find a circle which is contained in that curve? You can't, right? Because okay, so let me just write that down. So you're looking at R2. You're looking at R2 and take any curve, right? Any plane curve. Right, so this is in some sense a one-dimensional object. Right, so this is the set of all x comma y such that x square equal to y, say. Right, so you take any point on this curve, right? What is an open ball, or what is a neighborhood? A neighborhood in this case would essentially be a circle, right? Which is fundamentally a two-dimensional object, right? So can you find a circle of any radius, right? So which is completely contained in this curve? No, right?
What about if you shift that within the towards it?
Doesn't matter, right? Take any point. But on the other hand, suppose I defined the following set of all x, y, such that x square, let us say, is greater than y, or y is strictly less than x square, right? That's the entire set under this parabola, right? But not including the points. So what kind of a set is that? Is that an open set? Yes? How many say yes? How many say no? How many say yes? A clear show of hands. Okay. How many say no? What about the rest? Right. Okay. So take any point. All right. So this is the set. Right. So it's a set of all x comma y such that x square is greater than y. Correct. So let us take any point which satisfies this inequality. Correct. So take any x comma y in R2, all right, such that x square is strictly greater than y. Okay, so what does this mean? So this is, what does this set correspond to? It's basically this region, correct? But except the points on the curve. Okay, so now can you prove that this is an open set?
By x square comma z.
Okay, so what do I want to show? If I want to show that this is an open set, I have to show that every point is an interior point. And how do I show that a point is an interior point? I need to find some epsilon such that I draw an epsilon ball around this particular point. It should be completely within this yellow region. Correct? So now can you just find an epsilon which lies still in the region?
What you can do is pick any arbitrary point x or any arbitrary point.
So I'm starting with one point, right? Yeah. So maybe it's over here.
Pick take the perpendicular to the parabola from this point.
Okay.
And you measure the length of the perpendicular, and there's an epsilon ball with some distance minus the perpendicular length. Okay, is everyone accept? Does everyone accept that? No. Okay, let's try to find one particular epsilon. Right. It's okay. We can give some slack. Right. We don't necessarily have to look at the shortest distance or anything of that sort. Correct. So we know that x square is strictly greater than y. Right. So we picked the particular x. Correct. So can I find some room on the left and some room above and some room around it? Correct. That's what we want to know. So let me take x. So x square is strictly greater than y. Therefore, there is some delta greater than 0 such that x square plus x square is also greater than or equal to y plus delta. Okay, right? Or maybe x square equal to y plus delta. Okay, do you agree with this? Okay, so what does this say? There is this much of space above my particular point. Correct? At the same time, there is also, if I take x, so x square is greater than y. If I look at x minus some particular delta 1, this is equal to square root y. Okay, so that is kind of the space I have to the left of this particular point. So let me take, let's say, 1/4 of this distance. Okay, 1/4 of the minimum of these two. Right, so I started with one particular point. I know that there is this much of room, which is delta. Maybe let me call this delta 1 and call this, or let's call this delta y and delta x. Right, so this lies within this set. Correct? So let me take whatever 1/10 of this distance for all that matters, right? So let me take epsilon to be min of delta y delta x by 10. If I draw a ball of radius epsilon around my given point x comma y, is it going to lie within this set? Yeah? How do we know? Okay. So let's just look at x square. Is x square still greater than y or not? Right? So x square, okay, so now okay, my claim is that so a neighborhood of radius epsilon around this particular point x comma y lies completely in this set, right? So let me call this S.
This proof doesn't work if you take a point that is, say, below the parabola. If you don't have any value for delta x.
Which is below the parabola?
Like, for example, if you take 0 cross 0, 0 comma 0 here,
Yes.
then there's no delta x in this case. Right?
Why not?
It's below the, basically there's no,
Okay. So then you take x plus delta x.
like, if you have a delta y, you will not have any delta x.
Why not?
You can just mark 0 cross 0 on the graph.
Okay.
Yeah, take that one itself.
Take this particular point.
In
Okay.
this case, you have a delta y,
Okay.
but then there's no delta here, right? Okay, that's okay. Yeah, the minimum will be delta y. Yeah.
Yes. The minimum will be delta
Yeah.
y.
Delta x will be,
Yeah. So I'm sort of going on the right hand side
yeah,
of
this point.
of x, right? So okay, the general intuition is still the same.
Yeah.
Right? You find the closest point, as you mentioned, to the curve. Correct? Find the closest point to the curve. Let d be the minimum of the distance between xy the minimum distance between the point xy and a point on the curve. All right. Since it lies strictly within this set, there is a positive distance, right? This is strictly greater than 0. Do you all agree? Does everyone agree with this particular point? You just take a ball of radius d by 2 around x comma y. Does this lie within the set? Yes? Does everyone agree with that point? Or is someone not convinced? I see some more blank looks. Yeah. Correct.
How do you write it down?
How do you write it down as a proof? Okay. So which part is not fully formal at this point? It's mainly whether there exists a D, right? Suppose that there exists a D. Okay. You agree that the neighborhood of radius d by 2 lies completely within the set, right? Because after all, every point in the neighborhood is a distance at most d by 2 from x comma y, and the minimum distance to the curve is d. Right? So that point is fine. Now the only point you need to show is that there exists a minimum such point, right? Can you compute this?
Do that.
Yeah.
This is open. We'll have to show that. So we will take C as any point on the curve. So then D is the minimum, like the point that is closest to the curve, right?
Yes.
But if it's an open set, then there's no point that's like there will always be some point that's closer than the. Basically, there's no that point doesn't exist if it's open. Right?
No. That's not true. So the curve does not lie in the set, right? So more formally speaking, the distance to the curve is basically this quantity. It is the minimum of x minus x1 the whole square plus y minus y1 the whole square, such that y1 square equal to, y1 equal to x1 square.
The open set will be all those points that are.
So the set is basically the set of all points for which, so S is the set of all points x comma y such that x square is strictly greater than y. Right? So this is how I define my set. So visually, it is basically the entire region under the curve. Right? But analytically, this is the set. What is the minimum distance to the curve? It is, you want to find the closest point to x comma y which satisfies y1 equal to x1 square. So any point y1 equal to x1 square is a point on the curve. Correct? So all you need to do is find this. Right? Or in other words, this is minimum over all possible x1 of square root x minus x1 square plus y minus x1 square the whole square, right? And that is because I'm imposing the constraint that y1 equal to x1 square. That's a point on the curve. And this quantity is strictly greater than 0. Right? And why is that? X square is always greater than 1. So again, think about it. Right? Try to prove yourself that this quantity is strictly greater than 0. Right? If not, if you're not able to, then we can again discuss this in next class. All right. Any other questions? Okay. So we had this definition of what an open set is. And we had this notion of what is an interior point, right? And this notion of the interior point was used to define an open set. Right? It means that it doesn't really have a boundary in some sense. So similarly, we want to define points on the boundary in some sense. So we'll say that, so we'll define this notion of a limit point. So right? Okay. So we'll say that x is a limit point of A if the following holds. So take every open neighborhood, right? So take, no matter which neighborhood you take around x, this will always contain a point from A but not equal to x. Okay, it's a little complicated at first, Right, so let's go over it again. So we'll say that X is a limit point if every neighborhood contains a point in A but not equal to X. Okay, so let's see some examples. Let us just take the set 1, 2. Okay, let me take a point inside this set. Is this a limit point? Why not?
Because it's contained in A, because it's already contained in A.
So okay, so take any neighborhood. So let's take 0.5. Oh, sorry, let's take 1.5. Okay, take any neighborhood around 1.5. Does it contain some other point other than X but lies in A?
Yes.
It does.
Yes.
Right? If I take, let's say, 1.2, does this contain some point in A? Take any neighborhood around it. Does it contain some point in A but not equal to 1.2?
Yes.
It does. Right? So it is a limit point. All right? So let's look at something a little different. What about the point 1?
Yes.
You draw a neighborhood around it, any neighborhood around it. It doesn't have to be, again, the neighborhood does not have to be inside A. It should contain at least one point from A, but not equal to X. Yeah? So right now I'm just using the standard Euclidean metric, right? At least in R1, that's the only metric that we're using, so it's fine. Right? But of course, what is a limit point could potentially depend on what your metric is. But for most metrics, they won't change. Okay, so point 2, is this also a limit point? Yeah? Yes? No, the point X equal to 2.
Oh, so
Why is it not a limit point?
because we can have a neighborhood which can contain points from 1 and 2.
Okay.
So, and there won't be any point left within A, which is not in the neighborhood.
Why do you say that?
Because we can have a radius of
Okay.
from 2 and we can cover points till 1. There will be points in the radius greater than
It doesn't matter. So the neighborhood should contain some point in A, right? Other than X. Some point. It doesn't matter how many points are there. Right? So basically, you take any point. So this is my set S. In fact, any point in this set is a limit point. Right? So basically you have this interval, closed interval from 1 to 2. I take the point 2, right? I take this particular point, draw any neighborhood around it, right? It always will intersect with some part of 1, 2, right? And not including 2. So this is a limit point, right? Yeah.
So, like, for any set we take,
Correct.
unless the point we are considering is some random standalone point in the space, wouldn't it always be a limit?
Yes. In a way, you're right. So as long as it's not what is called an isolated point, as long as it's not completely far away from your set, or there's no other point which is close to this given point, it will be a limit point. And the reason why it's called a limit point is because you take any sequence
which converges to this particular point, right? So that sequence will have a limit, and this will be a limit point of that particular sequence, right? But anyway, so let's just use this as a definition for now. One subtle point is that the limit point need not necessarily be a point of your set itself. All right. So let me take the open interval from 1 to 2. Okay. Let me take any point inside this interval. Will it always contain, is it going to be a limit point?
Yes.
Yes. So everyone's convinced that that is going to be a limit point, right? So in other words, every interior point is going to be a limit point. Let me take the point x equal to 1. Okay. Is this going to be a limit point? Yes, it is going to be, right? Because no matter how I draw a boundary, how I draw a neighborhood around the point x equal to 1, it's always going to intersect with the set S. Right? So 1 and 2 are also limit points of this set S. What is not a limit point? Take any point which is outside this, right? Say 1.1 or 1.2. Okay, or what is slightly more interesting is take any point in the complement of this particular set. Is it going to be a limit point? It was. Sorry? Of this set, of the closed interval 1, 2. Yeah, so it will not have, so in any point in the complement of this closed interval 1, 2 is not going to be a limit point of 1, 2. Right? And one way to think about it is take any sequence in which lies completely in S. So pick any sequence of numbers within where all the numbers come from the set S, the closed interval 1, 2. Is it going to converge to something outside S? No, right? You can approach 2, but then that's it, right? It can only converge to 2, or it may not converge at all. It doesn't matter. But on the other hand, if I take a sequence in this particular set, can I construct a sequence which converges to something outside this particular set? I can, right? In particular, I can construct a sequence which converges to 2, right? And that number does not lie in the open interval 1, 2. So 2 is basically a limit point of S, right? Okay. Let's take a sequence itself, right? So let's take the sequence 1/2, 1/4, 1/8, and so on. Right? It's an infinite sequence. Yeah.
Like this one, any point on the real line will be a limit point for this set.
How?
Take any point on the real line.
Let's take x equal to 3.
But if we draw the neighborhood, x is equal to 3.
Huh.
Neighborhood of radius, any radius.
Yeah, every neighborhood should contain a point from A, not some neighborhood, right? Agreed? Okay, so let's take this. Yeah.
This,
Yeah.
So-
Which one?
the open set one.
Open set 1, 2.
So it's basically like there's a closed set on the one, then we are removing point.
Yeah.
So let's consider such a case where there's an interval, like a closed set,
Okay.
and then we are removing discrete points.
Sure.
So it can only, like the possible limit points are only the points that are removed and the
Correct.
points that are
Correct.
in the limit.
Correct. Yeah. That's right. Okay, so let's take S equal to this particular set. Okay, 1/2, 1/4, 1/8, and so on. In the previous case, how many limit points were there for this? Infinitely many, uncountably infinitely many, because every point in S was a limit point. What about this particular set? Infinitely many, right? But it also included points outside the set, right? And as you mentioned, you can also construct other interesting examples wherein you take a set, I remove some points from this, right? Let's say I remove 1.5, 1.3, 1.2, right? The limit points would be the set itself as well as those points that I remove, those discrete points that I remove. So now let's look at this particular set. It's a countable set, right? What are the limit points? Okay, complement of this, are you sure? So for example, 1.2, is it a limit point?
The 0.
0 is a limit point, right? Does everyone agree? You draw any neighborhood around 0, no matter how small it is, you will always have a point from S, right, in that particular neighborhood. Take any other point. Okay, what about the other points in S? It's not a limit point, right? Because let's suppose that I take this point x equal to 1/8, right? And let's say I draw a ball of radius, whatever, pick a number, 1/16 or 1/20 around it, right? This neighborhood will contain 1/8, but not any other point in this particular sequence, correct? So in this case, no point of S is a limit point. But 0 is a limit point.
Just one question now. If we take the set 1 to 2, open set 1 to 2, we take
The interval from 1 to 2.
yeah, interval 1 to 2.
Closed?
Either way doesn't matter.
Fine. Okay.
We take an arbitrary point inside that interval,
Okay.
and we drop the sequence that arbitrary point is there, x,
Okay.
and we take delta x tending to 0. We drop the set open set x minus delta x to x plus delta x as delta x tends to 0. So would x be classified as would x be a limit point or not?
I'm not sure I quite followed. So you take the open interval from 1 to 2.
You take any arbitrary x with
Take any point within that. Let's say 1.5.
and then
okay.
you define delta x tending to 0.
What do you mean? What is delta x?
Some
A neighborhood around it.
sorry.
A neighborhood around it, you mean?
Basically some very small then converging to 0. Okay.
Correct. So you're looking at some x in this particular interval,
Yeah.
1, 2, and you take the interval x minus delta x to x plus delta x.
And you remove this from the interval 1 to 2. So you're taking the set 1 to 2 slash
okay.
this.
Fine. You feel a constant delta x, right? Some positive delta x, right?
Some positive delta x.
Yes.
Okay, but
Okay.
then it will then it won't be
Yeah. Then x will not be a limit.
even if delta x tends to 0, it's still
Again, what do you mean delta x tends to 0? So delta x, you're removing some interval, right?
Yeah.
You have a neighborhood of
Yes, by 2, exactly. Yes.
Correct. So if you remove some interval from your given set, then the center of that interval will never be a limit point.
Yeah.
Okay.
Also, like, is it the case that limit points exist for like countable sets only if the sequence of number converges to a particular?
Yes. That's certainly a valid point. So if I give you a countable set, again, yeah, so if you can find a subsequence which converges to a particular number, then that particular point is going to be, again, it's a little more tricky, yeah, but I don't want to get into so much detail also. But yes, for example, I could take this is one set, S2 to be 1/3, 1/9, and so on. Take the union of these two, right? This will have two limit points, right? The limit, which is the limit of this particular sequence as well as the limit of this particular sequence. So it's a little subtle, but okay. So why am I defining all of these limit points? It's because the limit points can characterize two things. So in potentially you take any set, the boundary of that set is going to be a limit point, right? So therefore, which leads us to the definition of what a closed set is. So we say that a set A is closed if every limit point of A belongs to A. Okay, you have to be again careful with this. So one way to interpret this, interpret what a closed set is, you take any sequence of numbers from A or any sequence of points from A and find out where this converges to, right? If it converges, it is always going to converge to some point in A. It's not going to converge to anything outside, right? So in particular, let's take the set 1, 2. Is this closed? No. And why not? Right, because there are two limit points which are not in A, right? The point x equal to 1 and the point x equal to 2 do not lie in A. They are two limit points, and therefore, by the definition, it is not a closed set. Okay. What about the actual closed interval 1, 2? Right? If you take any point outside A, is it a limit point of A? No. Right? So every limit point is going to be inside A. What about the set 1/2, 1/4, so on? This is a convergent sequence. Is this a closed set?
Yes, 0.0. 0 is the only limit point in it. 0 cannot say.
How many say yes? How many say that this is closed? How many say it is not closed? Okay. Okay. What are all the limit points of this particular set? 0. So 0 is the only limit point of this particular set. The main confusion here is, does 0 belong to this set or not? Right? What is the set? The set is basically the set of all 1/2 to the n, where n is a natural number. Right? Does 0 belong to this set? For every natural number, you cannot construct a natural number which is such that 1/2 to the n is equal to 0. Correct? So it approaches 0 only in the limit. Right? Yeah, question. What is a sufficient condition? Which one? It's a definition, so it's if and only if. That is what a definition is. Okay. Let's look at something more interesting. So it's a set containing 4 points. 1, 2, 3, and 4. Is this a closed set?
Yes. Yes. Yes.
How many say yes? Okay, some hands up. How many say no? Okay, one or two hands up. Okay, if you say yes, why is it a closed set? Okay, so what are all the limit points of this? None, right? There are absolutely no limit points, because no matter which point you pick, either it is in this set. If you take any point in this particular set, it is not a limit point, because you can draw a ball around it. Take any ball of radius less than half, for example, less than 1 for that matter, right? That is not going to contain it. So that is not going to contain this A, right? So it has no limit points at all. And what does the definition say? If there is a limit point, it should be in A. If there are no limit points, no problem, right? So another way to interpret this definition is that A complement does not have limit points of A, which is the case, right? Question? It is closed. So this set is not closed. All right. Okay, so we have this notion of what a closed set is, and we know what the set of all limit points are. So the closure of a set of a set A will denote it by CL A. This is basically A along with all possible limit points. Right? So what is closure of the closed interval 1, 2? It is the closed interval 1, 2 itself. Question? Closed interval 1, 2. What is the closure of the open interval 1, 2? It is the closed interval 1, right? What is the closure of 1/2, 1/4, and so on? So it is this set along with 0. Right? Is the closure always a closed set?
Yes. Yes.
It is a closed set, right? So in other words, if your set is not closed, then by taking the closure, you are making it closed, right? So in some sense, if you had to define the boundary of a set, how would you define it intuitively? Yeah? Can you speak up?
Boundary of the set is limit.
Correct, but points inside can also be limit points, right? As we saw, if you take the closed interval from 1 to 2, 1 is a limit point, 2 is a limit point, but everything in between is also a limit point.
So minimum of closure.
Yeah? Okay, so if you had to take the closed interval 1, 2, what is the set of all boundary points? 1 and 2, correct? What have you removed from this set to make it the boundary? The interior points, right? So in other words, the boundary points So BD of A is simply the closure of the set, and from that closure you remove the interior. So in other words, if I take the set open interval 1 comma 2, right, what is the boundary equal to? It's still 1 comma 2, right? By this definition, this is how I define the boundary. The boundary need not be a point inside the set, right? But certainly it encloses the set completely. Correct? If I had to take this example that we had in the very beginning of the class, so the set of all x comma y for which y is less than x square. Again, intuitively, what would the boundary be? It's basically the parabola itself, right? The curve, right? And that is that you can see that indeed, right? Because what is the closure? It is the entire set along with the curve. So the boundary should indeed be the curve. So it is the closure minus the interior. Correct?
Can points lying on the parabola can be called limit?
Exactly. So every point on the parabola is going to be a limit point, but it's not an interior point, right? Any questions? So the reason why we are going to these lengths to define what is a closed set, why are we so precisely defining what closed sets are and so on, is mainly because when we are doing optimization, convex optimization, in many cases we have guarantees only if the set is closed, when the set is convex and so on, right? So this is one step to defining the objects or the conditions under which we can optimize a particular function, right? And we'll see that in a little bit. So there's another notion of compactness. There's a more complicated definition, but for our purposes, we'll only be looking at subsets of Rn, right? So so take any subset of Rn, we say that it's compact if it is closed and bounded. This is not the definition of a compact set, right? So you can look up the notes online and that has the exact definition of the compact set. But for all our purposes, you take any closed and bounded subset of Rn, that is going to be compact. Okay? So what is a bounded set? Again, you have a metric, right? So how would you define a bounded set?
All points. We can define limits of the
Of? Okay, intuitively, what do you mean by a bounded set? Yep, so there should be some upper bound on the distance between any pair of points within your set. Correct? So as long as xy, so as long as this is less than infinity, the point is bound. So there is some number, let's call it m. The distance between every pair of points is less than or equal to m, right? Then it's bounded. Correct? So suppose I take a particular function, right? You want to know if that function is bounded or not. If I take f of x equal to x square, right? Is this function finite? Is it finite? For every x, is y finite? For every x in R, is y of x finite?
Yes.
It is, right? It's a finite, the function is finite, but is it bounded? It is not, right? Because you cannot put an upper bound on the value of f of x, all right? Okay. Okay, so we'll switch to another topic of continuity, right? Again, something you've seen before. So when you say that a function is continuous, yeah.
Limit exists at 100.
Okay, so basically, if you take any x, so you have a function f from one set to another set, if f of x is equal to limit y tending to x, f of y, the function is said to be continuous. Right? Why this is important is because if a function is continuous and it's defined over a compact set, then it always has a well-defined maximum and a minimum. No matter what you do, no matter how weird a function you try to cook up, as long as you have these two basic guarantees, the set is compact and the function is continuous, it'll have not just a supremum and an infimum, it'll have a maximum and a minimum. So the maximum and minimum will be achieved within points in that particular set. So there could be multiple points of maxima and minima. Doesn't guarantee about how many points are going to be there, but there will be a point, right? But if any of these conditions are not are violated, then you cannot guarantee anything. Okay, so for example, suppose let's take a situation where one of these conditions is violated. The set is not compact, but f is continuous. Can you give an example where the maximum is not achieved or the minimum is not achieved?
X squared.
Okay, so f of x equal to x square, and the set x is the set of all reals, right? So in this case, there's no maximum, right? It's an unbounded function, and therefore but the function is continuous. So now can you give an example of a compact set? Let us take, yeah. What, that maximum does not exist? The tools that we have right now are not sufficient. It is very involved. If you want to prove it formally, it is quite involved, right? Because over here I've not really defined compactness. You need the actual definition of a compact set, and that property, and along with a couple of other results, are required to prove that this holds. Right? So this is also called the extreme value theorem. If you pick up any decent book on real analysis, it will have this particular theorem. Right? So in particular, since what happens is that if you take X, right? So it's compact and F is continuous. It turns out that the image of X, or in other words, the range, is also compact. So that is closed and bounded, and therefore it's a subset of the reals. Therefore it has a well-defined maximum and a minimum, and therefore it is. But of course you should be able to prove that f of X is also compact. That is what takes work.
The conditions where the sets are like not closed and bounded, but the set is still not compact. The definition that we are having.
Yes.
Is it just
if you look at any subset of Rn, it's an if and only if condition. It is compact if and only if it is closed and bounded. But you can have other spaces where whatever boundedness does not necessarily imply compactness. But anyway, that's something separately which I don't want to get into. So in particular, boundedness does not necessarily guarantee compactness in certain other spaces. Fine, that's that aside. Now can I construct, okay, can we come up with a different example, right? A set which is bounded but not closed, and yet the maximum and the minimum f is continuous, but max or min does not exist. So X is whatever not closed, but bounded, and F continuous.
Equal to X over open interval of 1.
One at a time.
if it's X square and interval is open interval?
F of X is X square. Okay. Equal to X square in the open interval 1, 2. There's no maximum or minimum, right? Because the maximum, the supremum is 2. Sorry, the supremum is 4, achieved at 2. The infimum is 1, achieved at 1, and both are not in this. You have another example?
Say y equal to X.
Sure. Yeah. Take it easy. Right? In fact, something more tricky can happen, and that is the function may not even be bounded. Exactly. So if you take f of X equal to 1 by X, X in 0, 1, it's well defined at every single point. It is continuous, right? But this is an example where, since it's not closed, right? This set is closed and bounded. This set is bounded but not closed. So the range is not bounded, right? But on the other hand, if you try to, if this set were indeed closed and bounded, it's impossible to construct a continuous function which is not bounded. It's a surprising, may seem a bit surprising, but But that's it.
You can have periodic functions in that case, right? For example, if you take the interval, if you take tanh function,
Okay.
you set the limits, you set the bounds to be the period the bounds are when it repeats. For example, it repeats minus pi by 2 to pi by 2. In
Okay.
that case, it is unbounded, right?
Okay, but are you defining it at pi by 2? What happens at pi by 2?
It's infinity.
It's not real, right? It's not defined. It's not defined.
Yes.
So it's defined in the open interval from minus pi by 2 to plus pi by 2. You can try. You won't be able to. All right. Okay. So that's maximum. Yeah. All right. Now, if it's closed and bounded and the function is not continuous, can you come up with an example? So f not continuous, but x is closed and bounded. The step function, how would you define the step function?
0 at like 0.
Okay.
1 at x.
Okay, but this has a maximum and a minimum, right? I want an example where there is no maximum or there is no minimum.
Construct an arbitrary. Like
Yeah.
I take minus 1 to 1.
Yes.
Closed.
Yes.
I'll take f of x equal to mod x. But at 0, I can say f of x.
Yeah, exactly, right? So you take any function at maybe one endpoint, you just redefine it as something else. So for example, take f of x equal to whatever x for x maybe less than 1, but 0 for x equal to 1, and the set x is whatever 0 closed interval 0 to 1. Right? The supremum of this function is 1, but that is never achieved because at x equal to 1 I'm redefining it as something else. Right? Again, these seem pathological examples, but you have to be careful. For example, if you have a function that you're trying to optimize over and you don't have any of these guarantees that the function is continuous or the set that you're optimizing over is not closed, and you try to say run a particular solver to optimize over this, you could get completely wrong results and you don't know why you're getting it. Right? And that could be because, well, there exists no maximum or a minimum, or that is or it's not achieved at any particular point. It could be an unbounded function at some particular point. All right. So let's maybe look at some slightly more interesting examples. So suppose I give you a set of points, right, in Rn. Let's say x1, x2, some xm, xi in Rn, and I define this set S, which is sometimes called the convex hull of these points, which is the set of all possible convex combinations of these points. Set of all x, which I can write as alpha 1 x1 plus alpha 2 x2 and so on up to alpha m xm for some alpha 1, alpha 2 up to alpha m. So each alpha I is between 0 and 1, and the sum of all the alpha i's is equal to 1. Right? So this is called the convex hull of these points. We'll see convex hulls later on, but what kind of a set is this? Is this an open set? Is it a closed set? Is it a compact set? Okay, let's get rid of the easier ones first. Is it a compact set? Or firstly, is it a bounded set? Everyone agrees that this is a bounded set, right? Because you take any point in S, right? It's a sum of some linear combination of these points, right? So therefore, the norm of any vector in this set is at most the sum of the norms of these vectors, right? Because each coefficient can only be between 0 and 1. So therefore, the norm is bounded by some particular quantity, the sum of the norms of the m vectors, and therefore the set is bounded. Okay, so this is bounded. Is it closed? Okay, maybe let's just try to visualize this particular set. Okay, that will help. So what am I doing? I'm taking, let's take R2 because that is really where things are interesting. Or let's start with R1 to build intuition. So I have m points, right, which are basically points on the real line. I have m points. So this is my x1, x2, x3, x4, and x5. What will a convex hull be equal to?
Points between x1 including x1 and x5.
So to expect.
The interval from the closed interval x1 to x5. Does everyone see this? So you take any 2 points. The convex hull is basically just alpha x1 plus 1 minus alpha x2, right? According to this particular definition, right? Similarly, generalizing this, the convex hull of these points x1 to x5 is basically you take the minimum point, you take the maximum point, the interval joining these two will give you the convex hull. Okay, try to prove this. I leave that as an exercise. Okay, now let's try to look at R2, right? I have plane, I take a bunch of points. These are my points, x1, x2, x3, x4, x5, x6. What would the convex hull look like? Yeah?
Variance at the pentagon of the top.
Yes. So, okay. So let's look at this particular statement, right? You take any 2 points, right? Any of these 2 points, take the straight line joining these two. Will it lie inside the set?
Yes.
It will, right? Because the straight line joining these 2 points is, say, alpha xi plus 1 minus alpha xj, correct? And that certainly satisfies the conditions over here, right? So you take this point, the straight line joining these 2 points is going to lie in this set. So certainly these points are going to lie in the set S, in the convex hull. What about the other points? If I take a point over here and any point over here, is the straight line joining these 2 points also going to lie in the convex hull? Although it may not be immediately obvious, that is indeed the case. So in other words, this entire region is going to lie in the convex hull. Okay, so sit down, try to work it out, right? You can only do it if you put pen on paper, right? But this is the convex hull. Okay, the claim is that this is a closed set. Okay, again I won't prove it over here, but this is a closed set, right? So we have a couple of minutes. So one more point. If a set is closed, right? So you have an example of a closed set, right? Which is the closed interval 1, 2. That's an example of a closed set. Any closed interval is a closed set. If you take a finite set of points, is it a closed set? Finite points in Rn. It is, right? If I take a countable set of points in Rn, will it be closed? Countable. May not be, right? Because R, whatever you take, right? Because we took that sequence, right? The sequence, take a convergent sequence, say 1, half, 1/4, and so on. Then it has a limit point which at 0, but that's not contained in the set. So it's not a closed set, right? But is it an open set? Which one? 1/2. Is it an open set? What are the interior points?
Okay.
Yeah, so it has to have a neighborhood with, so every point should have a neighborhood around it which is contained in the set, right? Countable sets are not open, cannot be open. Right? Finite sets are closed. Countable sets may be closed but may not be closed. Countable sets are never open. Finite sets can never be open. Can you give an example of any other set which is neither closed nor open?
Half open.
Yeah, take a half open interval, right? So 1, 2. This is neither closed nor open, right? Is there a set which is both open and closed?
If we take minus infinity to be belonging to the set, then we can define.
And minus infinity and plus infinity do not belong to the set. So right now we have seen examples of sets which are closed but not open. If you take the closed interval 1, 2, it is closed but it is not open. You take the open interval from 1 to 2, it is open but it is not closed. You take the half open interval 1, 2, closed at 1, it is neither open nor closed. Is there some subset of R which is both open and closed? Yeah? The null set is certainly an example of a set which is both closed and open, which is R. So take any point of R, is it an interior point? No matter which point you take, in fact, any neighborhood around that point is also a point in, also is contained in R. Is it a closed set? Is every limit point of R also a point of R? It is, right? So R is both closed and open.
There are sequences that we say if they converge.
If they converge, yes. So an unbounded sequence is not a convergent sequence. You say that it converges to infinity to a sense, but it's a divergent sequence. It's not a convergent sequence. Right. So you have to be careful. Also, if you take any open set, the complement is always a closed set. If you take any closed set, the complement is always an open set. And that extends to R as well. So you take R, what is the complement of R? The empty set, the null set, which is open. Similarly, R is also a closed set. The complement is the null set, which is closed. Right? Okay. So let's stop here. Again, I've updated the lecture notes in the website. So please go through that. There are some points which I may not be able to cover in class. Again, they're finer details, but certainly are helpful. Okay.